An ideal op-amp is imagined to have an open-loop voltage gain, a sub-OL, that is infinitely large. The basic relationship is V sub out equals a sub-OL open parenthesis, V plus minus V minus close parenthesis. If a sub-OL tends to infinity while V sub out stays at a realistic finite value, the power supply limits. The only way the product can stay finite is for the differential input voltage, V plus minus V minus, to become essentially zero. Mathematically, we write the linear approximation V plus approximately equals V minus for any finite V sub out. Think of a seesaw with a huge lever arm. Even a tiny weight difference makes it tip dramatically, so the system quickly forces the two sides to be level. In circuit analysis, we treat this as a constraint that the two inputs are at the same voltage, which dramatically simplifies calculations. Real-world note: real op-amps have a sub-OL in the range of 10 to the 5 to 10 to the 6 at low frequencies, which is large enough that the approximation is usually accurate for most linear applications. Input impedance is the opposition a device offers to current entering its pins. For an ideal op-amp, Z sub IN equals infinity. Consequently, the current that flows into either the non-inverting plus or inverting minus terminals is zero. I plus equals I minus equals 0 amperes. A helpful analogy is a perfectly insulated door. No one can pass through it, yet you can still sense the pressure on each side. Because no input current is drawn, the op-amp does not load the preceding stage. The voltage it sees is exactly the voltage present in the circuit before the op-amp. Practical example: in a voltage follower configuration, the source sees the same voltage after the op-amp as before because the op-amp does not draw any current from the source. Real devices. Typical input bias currents are in the picoampere range for BJT input stages and femtoampere for CMOS input stages, which approximates the ideal case for most low-frequency designs. Zero output impedance means the op-amp can be treated as an ideal voltage source. Its output voltage does not sag when a load draws current. V sub out equals V sub source, Z sub out equals 0. If you connect a resistor R sub L to the output, the current I sub L equals V sub out divided by R sub L flows, yet the voltage remains exactly V sub out. Imagine a perfect water pipe that maintains constant pressure no matter how many taps are opened downstream. The pressure voltage never drops. Application: in a non-inverting amplifier, the gain formula 1 plus RF over RG is derived assuming the output voltage is applied directly across the feedback network without any voltage drop inside the op-amp. Reality check: real op-amps have a small output resistance, a few ohms. For typical load currents less than 10 microamps, the voltage error is negligible, but heavy loads may expose this non-zero resistance. Explanation: the ideal op-amp is imagined to have unlimited bandwidth and an infinite slew rate. Bandwidth refers to the frequency range over which the gain stays constant. In the ideal case, the gain does not roll off, so the magnitude response is a flat line from DC to infinitely high frequency. Slew rate SR is the maximum rate of change of the output voltage. SR equals dV out over dt maximum. For an ideal device, SR tends to infinity, meaning the output can follow any input step instantly, like a perfect light switch that turns on with no flicker regardless of how quickly you flip the lever. Example: a square wave input of amplitude Vp and frequency f would be reproduced exactly at the output, no matter how high f is, because there is no gain bandwidth limitation and no slew rate induced rounding of the edges. In practice, real op-amps have a gain bandwidth product GBWP of a few megahertz to gigahertz, and slew rates from a few V per microsecond to thousands of V per microsecond. Designers must check that the required frequency and edge rate fit within these limits. A perfect differential input means the op-amp amplifies only the voltage difference between its pins and completely rejects any voltage that appears equally on both pins, common mode voltage. The common mode gain a sub Cm is 0, so the common mode rejection ratio CMRR is infinite. CMRR equals a sub DIFF divided by a sub C, M tends to infinity. Imagine two people standing on a moving walkway, the common mode. The op-amp cares only about how far apart they stand, the differential, not how fast the walkway moves under them. Mathematical view: if V plus equals V minus equals V sub Cm, then V out equals a sub OL times open parenthesis, V plus minus V minus close parenthesis equals 0. For any finite a sub OL, hence, a perfectly balanced input will never produce an output. Real life, typical CMRR values are 80 to 120 decibels, which means common mode signals are attenuated by a factor of 10 to the 4th to 10 to the 6th, good enough for many sensor interfaces but not truly infinite. Explanation: offset voltage is the small differential voltage that must be applied between the inputs to make the output 0 when it otherwise would not. In the ideal model, this offset is exactly 0, and the input bias currents, the tiny currents required to bias the internal transistors, are also 0. With V sub OS equals 0 and I sub B equals 0, the following holds true. V out equals a sub OL times open parenthesis V plus minus V minus close parenthesis, with V plus equals V minus implies V out equals 0. A useful analogy is a perfectly balanced scale. No matter how you place identical weights on each side, the pointer stays exactly at 0. Consequences: in DC gain circuits, for example an integrator, any small offset would integrate over time, causing the output to drift to the rails. Setting V sub OS equals 0 eliminates this drift. Practical numbers: real op-amps may have offset voltages of a few microvolts to several millivolts and bias currents from picoamps to nanoamps. Precision op-amps are selected when low offset is critical. Power supply rejection ratio, abbreviated PSRR, measures how changes in the supply voltages plus V and minus V affect the output. An ideal operational amplifier has infinite PSRR, meaning the output is completely immune to any ripple, noise, or drift on the power rails. PSRR equals delta V supply divided by delta V out, approaches infinity. Think of a noise-canceling headphone. It can completely ignore background sounds and let you hear only the music. Similarly, an ideal operational amplifier ignores supply noise and reproduces only the wanted signal. Design impact: because the output does not depend on supply variations, designers do not need to add extra filtering or regulation for the op-amp itself. Reality: real operational amplifiers have PSRR values of 80 to 120 decibels at low frequencies, dropping at higher frequencies. In precision circuits, a clean supply is still recommended. Inverting amplifiers: assume I minus equals 0, V minus equals V plus equals 0, grounded non-inverting input. KCL at node V minus. Open parenthesis, V sub in minus V minus, close parenthesis, divided by R sub in, plus, open parenthesis, V sub out minus V minus, close parenthesis, divided by R sub F equals 0. Since V minus equals 0, V sub in divided by R sub in plus V sub out divided by R sub F equals 0, implies V out equals negative R sub F over R sub in times V in. Non-inverting amplifiers: assume I plus equals I minus equals 0, V plus equals V in. Voltage divider at the inverting input. V minus equals V out times R sub G divided by open parenthesis, R sub G plus R sub F close parenthesis. Because V plus equals V minus, V in equals V out times R sub G divided by open parenthesis, R sub G plus R sub F close parenthesis, implies V out equals V in times open parenthesis 1 plus R sub F over R sub G close parenthesis. These equations are exact as long as the ideal rules hold: infinite gain, infinite input resistance, 0 output resistance. They are the foundation for countless analog circuits such as filters, oscillators, and instrumentation amplifiers. Note any deviation from ideal, finite gain, input bias, etc. Add small error terms that can be derived by substituting the real parameters into the same nodal equations. Explanation: the virtual short is a direct consequence of infinite open loop gained together with the linear approximation. It states that the two input terminals are at the same voltage, V plus equals V minus, without being electrically connected. This enables the use of Kirchhoff's current law, KCL, at the input node while treating the voltage as known. Illustration. Step 1. Apply a voltage Vin to the non-inverting input. Step 2. Because a sub-OL is infinite, the operational amplifier drives its output until the inverting input node is forced to the same voltage as the non-inverting node. Step 3. No current flows into either input, I plus equals I minus equals 0, so all current that enters the inverting node must leave through the feedback network. Using KCL at the inverting node for an inverting amplifier gives the familiar gain formula derived earlier. The virtual short allows us to replace a complex active device with a simple voltage constraint, greatly simplifying circuit analysis. Real-life tip: when designing high-speed or high-precision circuits, the virtual short is only approximate. Finite gain causes a small voltage difference, V plus minus V minus equals V out over sub OL. Engineers sometimes include this term to predict error. Explanation: below are 3 typical exam-style questions that test whether a student correctly applies the ideal op-amp assumptions, followed by the reasoning behind each answer. Question 1: a 10 kilo ohm resistor R1 connects the input voltage Vin to the inverting input of an ideal op-amp. Period. A feedback resistor RF equals 50 kilo ohms connects the output to the same inverting node. Period. The non-inverting input is grounded. Period. What is V out in terms of V in question mark? Answer: using the virtual short V minus equals 0 and input current equals 0, KCL gives V out equals negative RF divided by R1 times V in equals negative 5 V in. Why it matters: the student must invoke infinite input impedance, no current into the pins, and the virtual short to write the node equation. Question 2: an ideal op-amp is powered from plus minus 15 volts. If the supply voltage on the positive rail suddenly drops by 1 volt due to a line glitch, what is the change in the op-amp's output voltage? Answer: 0 change. Infinite PSRR means the output is completely unaffected by supply variations. Why it matters: checks understanding of PSRR arrow infinity, and that the output depends only on the differential input, not on the supplies. Question 3: in a non-inverting amplifier, R1 equals 2 kilo ohms and R2 equals 8 kilo ohms. The op-amp has a finite open-loop gain of OL equals 10 to the 4th. What is the actual closed-loop gain? Answer: ideal gain equals 1 plus R2 divided by R1 equals 1 plus 8 divided by 2 equals 5. With finite OL, the closed-loop gain G is G equals a OL divided by open bracket 1 plus a OL divided by open bracket 1 plus R2 divided by R1 close bracket approximately 10 to the 4th divided by open bracket 1 plus 10 to the 4th divided by 5 close bracket approximately 4.9998. The error is tiny, illustrating that the infinite gain assumption is usually safe, but can be quantified. Why it matters: forces the student to recognize the limit of the ideal model and calculate the small deviation caused by finite gain. Takeaway: mastery of the ideal model provides a powerful mental shortcut for designing and analyzing analog circuits, while awareness of its boundaries ensures accurate real-world designs.